Everyone, my name is Trilochhan Bhatta. I am from Micro Nano Devices and Packaging Laboratory, Kwangwoon University. Today I will discuss about the IPD measurement techniques, which is chapter 5 of our course book, Practical Integrated Passive Device Technology. And I will include the basic concept of IPD, and then I will discuss detail on the IPD measurement techniques, in which I will discuss in three major aspects of IPD measurement, which are on-wafer measurement, power handling measurement, and process control monitoring. So in case of on-wafer measurement, I will discuss the key components of microwave on-wafer test systems, in which I will discuss about the network analyzer, spectrum analyzer, RF probes, and RF connectors and adapters, and many more. And finally, I will conclude my presentation. So, talking about the basic concept of IPD, IPD stands for the integrated passive devices. So, in which we include only the passive components such as resistor, inductor, and capacitor chips into ICs. So this is the integration of individual passive components into a microwave system, and the IPD leads to the transformation of RLC chips into the ICs, so we can achieve high circuit density, we can miniaturize the size, and we can also minimize the crosstalk by this IPD technique. So the IPD is the bridge platform between the front and the back ends of the semiconductor industry, and have wide application in many different fields such as mobile handsets, GPS, and radar system, broadcast system, and in satellite communication system. So these two figures are the GSM DCS transceiver sizes comparison by using two techniques, and where the first one is the discrete SMD technique, and the second figure is the integrated passive device technique. So we can see from these figures, in the discrete SMD case, the large number of passive components, they are distributed along this board, and if we see the same number of RLC components by using IPD technique, we can see how the size is miniaturized into a single IC using IPD technique. So in this way we can miniaturize the size of the RLC chips into small ICs, and we can achieve the high circuit density as well as can minimize the crosstalk, because in this case the loop area is very small in compared to the discrete SMD. So these kind of IPD techniques are very important in case of the miniaturization and minimizing the crosstalk. So the IPD measurement techniques, why we need IPD measurement techniques, and what are the key IPD measurement techniques. I will include these things in this slide. To manage the overall performance of IPD, all the components we need to characterize accurately, and for this we need to use the precise measurement techniques at the component level, because the poor measurement of the device undertakes that can lead to the bad results, such as the wastage of both time and money. So in this case we need to have the good understanding of measurement techniques and measurement equipments for subsequent modeling. And there are three major aspects of the IPD measurement, which are the on-wafer measurement, power handling measurement, and the process control monitoring, PCM. So in case of the on-wafer measurement, it investigates the true performance of the device, not the device plus package. So it is only used for investigating the performance of the device. And in the power handling measurement deals with the power levels beyond which damage may occur in the IPDs. So however, the power handling level or power level for the device under test are usually well beyond the dynamic range of the system, although we need to find the power levels of our device under test to minimize the damage. And another important aspect is the process control monitoring. So process control monitoring deals with the processes followed it in order to obtain the detailed information about the process used during the IPT measurements. So in the measurement technique, the first important aspect is the on-wafer measurement. So in these slides I will include why on-wafer measurement is required. So in order to investigate the true performance of the device, not the device plus package, which I already mentioned in the previous slide. In this case, the DM reading is possible, but this may lead to additional errors and uncertainties. So to determine whether the good dies in the good dies and to reduce the packaging cost, the on-offer measurement is used. And another important thing is it can automate the measurements because it's able to test wafers automatically. So this is the cost effective and fast method of of the IPT measurement. And here we can see the typical on-offer measurement system, which consists of many important components which are integrated to form this whole measurement system. So the key components which I will discuss briefly in this presentation are the network analyzer, spectrum analyzer, probe station, RF cable, RF connector and adapter, and RF probes. So talking about the network analyzer are very important tools in case of the RFIC and RF device measurement. This network analyzer measures the response of the network as a vector. So the response have the real as well as the imaginary parameters, and this characterizes the performance of the device under test in frequency domain using its own stimulus to the duty. So while measuring the device under test, this network analyzer uses its own stimulus, its own signal, which is generated from the signal generator in order to characterize the performance of the device. And the transfer functions are the most common measurements, which are in the logarithmic vertical scale, and horizontal axis shows the different parameters such as frequency, phase, group delay, real or imaginary part of the transfer function. This network analyzer measures the transmission and the reflection measurements, where the reflection measurements characterize the input and or output behavior of the device under test. And for this it requires special accessories such as directional coupler, bridge, or S parameter test set. And the network analyzer can give the measurements related to the reflection data, return loss, reflection coefficients, isolations, impedance, and standing wave ratio parameters. So the network analyzer are of two types, basically the scalar network analyzer SNA and the vector network analyzer. So this is the typical figure where it shows the two-port network analyzer with device under text. So in this case the port 1 is used at the input of the DUT, and port 2 is used at the output of the device under test. And in case of the scalar network analyzer, it can only measure the magnitude, so we cannot obtain the phase parameters in this case. And as these scalar network analyzer perform the transmission measurements by means of a diode detector. So there is one diode detector which converts the RF signal into the DC voltage. So DC voltage is the measure signal here, which is proportional to the magnitude of the RF signal. So in this way we can measure the magnitude of the RF signal based on the DC voltage signal. And in case of the vector network analyzer, we can measure both amplitude and the phase, so we can obtain the phase parameter also. And as I already mentioned, the input of DUT is connected to the cable that is connected to the port 1 of the vector network analyzer, and the output is connected to the port 2 of the vector network analyzer. And the vector network analyzer, it measures the transmitted and reflected waves as a signal passes through the DUT. So here we can see the here is the device under test. So signal, or we can say the stimulus signal, is generated by the generator of the VNA, which is the input signal for the device under test, and the receiver collects the transmitted signal or output signal and the reflected signal, and display in the which is displayed in the PC or display devices. So this is the typical figure of the vector network analyzer, which can operate between the 45 MHz to 50 GHz frequency range. And here we can see in the block diagram, working block diagram. So incident power is applied in the form of the stimulus to the device under test at port 1, and transmitted power and the reflected power are the measurement. And also for the two-way systems, the incident power is applied to the port 2, and transmitted power and reflected power are measured. So this is the typical measurement characteristic for the, or we can say the network analyzer measurement for transmission characteristics, which shows the vertical axis as the transmittance parameter that we call S21 parameter in log magnitude scale, and the horizontal component is the frequency. So the signal has the frequency range of 6 GHz to 14 GHz in this case. Another important component is the spectrum analyzer, which is used for measuring the magnitude of the input signal against the frequency. And by observing the signal in the frequency domain, we can get information about the variables such as the harmonics, the signal width, and any spurious content of the signal. So when comparing the basic fundamentals about the spectrum analyzer and the vector network analyzer, spectrum analyzer analyzes an input and input applied signal, whereas the vector network analyzer, it creates own stimulus, and which is used to characterize the DUT. So the spectrum analyzer is used to measure the carrier power level, noise, and harmonics. And in case of the vector network analyzer, it is used to measure multiple parameters, such as especially related to the S parameters, which are the reflection loss, insertion loss, S parameters, and the transmission loss and return losses. In case of the spectrum analyzer, the horizontal component is frequency, whereas in case of vector network analyzer, the horizontal component can be any of these. So frequency, phase, group delay, real or imaginary part of the transfer function. So one of the important component of the on-offer measurement system is the probe station. So this figure illustrates the detailed components of the probe stations. The important components are the optical devices such as microscope, the chalk, which is used to move the wafers from die to die, and the stage is another important components. So here are micro manipulators, which can detect the small amount of vibrations and can in X, Y, and Z motions. So this is the typical probe station. And probe station, major function of the probe station is to allow us to position the RF plugs on the silicon wafer, so that we can test the device. and this also allows the device to hold a wafer or die and use the stage to precisely position the device. So depending upon the how the chalk is moved and how the wafer is loaded, probe station are two types. One is the manual probe station, which is especially used in case of the laboratory testing, where the wafer loading and the chalk movement is manual. And another type is the automated probe station, which is equipped with the computer automation system for the wafer loading as well as for the chalk movements. And in this case, this kind of automated probe stations are especially used in the manufacturing processes, where or we can say the in case of the production, where the speed is demanded. So this is the basic working principle. At first the wafer is placed on the chalk, where chalk is slightly larger than the wafer, and this chalk moves the wafer from die to die. And the jet motion mechanism rises and lowers the chalk height with respect to the probes, where the probes are fixed to the micro manipulator, and the micromanipulator enables the fine movement in x, y and z dimension. So since the minute vibration can cause the probe to vibrate on duty pads during RF test, so in order to minimize the external vibration, entire probe station need to be placed on the vibration damping table. And as I already mentioned, if chalk movement and the duty measurements are manual, then it is the manual probe station. And here the chalk movement and the duty measurements are automated using computer automating systems, then this is the automated probe station. So the RF cable are the important components in the one of our measurement system, whose main purpose is to connect the test system to the device under test. So for perfect connection and minimum loss, the RF cables having high voltage standing wave ratio and the minimum insertion losses are demanded. Also the minimum inductance is required. So to minimize the inductance, especially low dielectric core and the conductive surfaces in the outer diameter of the center conductors are used. And these RF cables are typically of two types commonly in use. They are semi-rigid type and the flexible type. So in case of the semi-rigid type, as you can see in the figure, they have the solid aluminum or copper jacket over the semi-flexible dielectric, which protects the solid conductor. Whereas in case of the flexible cable, it has a more complicated arrangement of plastics or plastic encased, and the aluminum braided shielding is used over a flexible dielectric covering the standard center conductor. So one of the important property of a good RF cable is to have good flexibility, that is the flexible outer skin, and have the smooth conducting surface, because in case of the bending, especially the semi-rigid cables the bending of the semi-rigid cable can cause the microscopic cracks, and this may lead to the unreliable ground connections. So due to the physical motion and the bending of RF probe, it can lead to the intermodulation distortion and the phase changes as well as the insertion losses. So these days some phase meshed cables are available, which can be used to minimize these losses. The RF connector and adapters are another important parts of the on-offer measurement system. So main purpose of the RF connector is to make the electrical connection for signal transmission in the RF application. For measurement applications, the number of connects and disconnects impact the lifespan of the connector in use. So if we need if we need the usable frequency larger, then we need to decrease the diameter of the outer conductor, whereas if we need the lower frequency, the air space is filled with dielectric. However, in this case it increases the insertion loss. So there are three different types of RF connectors which are commonly being used in the RF applications. Those are the BNC, SME and SMB connector types. So before discussing detail on these connector types, let's discuss on the adapter. The main purpose of the adapter is to provide the transition between connector types and the genders. As we all know, there are two different type of connectors, like male connector and female connector. So adapter provides the transition between these two connector types, and the adapters are generating very low reflections are preferred in the measurement system. So talking about the RF connector types, so we can see here is the BNC connector, which is used for very low frequency RF applications up to 4 GHz, and especially used in the video signal and timing signals. And the SMA connector, they are quite used for quite high frequency up to 18 GHz, and are very mostly used in the many RF applications such as power amplifiers, isolators, power splitters, directional couplers, and in the GSM CDMA, as well as in low power UHF communication system. And the another type is the SMB, and this is a rigid kind of RF connector, and has the intermediate frequency in between these two BNC and SME, which is up to 10 GHz, and the application includes the medical equipments, base stations, and low power UHF communication system. So RF probe is one major component of the on-offer measurement system, which makes the physical connection with the DUT. So RF probe is the only and final link in the RF test system, which directly connects with the device under test, and the major role is to form the connection between coaxial cable and the probe pad. In this case, the probe's connector is hooked to the RF test system, and the probe tip touches the probe pad on the wafer surface. So there are different configuration which depends on the die's probe pad layout and the die's RF function. So in this case, you can see three different configuration for the RF probe. Yes, GSC configuration, GS and SC. So this configuration of the RF probe, they require at least two conductors, signals and the grounds. However, the position can be different, and these are the structures for the RF probe tips. So up to now I discussed about the major components of the on-offer measurement. So after that we need to calibrate the measurements so that we can compensate any imperfections that may be found in the test system. And in this case we used some known quantities to measure, and these quantities are called the standards, and each standard is precisely characterized to its magnitude and phase over frequency. So by measuring these standards in place of the device under test, we can calibrate the RF path so that any inherent errors in the test setup can be compensated. There are three main methods, calibration methods, which are commonly being used, and those methods are SOLT calibration, TRL calibration, LRM, or we also say the LRRM calibration. So in case of the SOLT calibration, where S stands for short, O for open, L for load, and the T for through, this is the broadband calibration method, which can be used at up to frequency of 110 gigahertz, and this is widely used method. So in this case, the probes are fixed, and reference impedance is set by the trimmed resistor. So in this case, the parasitic characterization is little bit difficult. And in case and another method is the TRL method. So here T stands for through, reflect, and the line, R for line, and L for R for reflect, and the L for line. So this is the simple standard and no parasitic characterization. However, this is not the broadband technique. So and also the fixed, we cannot have the fixed probe here, and this method leads to some dispersion problems. The another method is calibration method is LRM or LRRM calibration method, where R stands for the reflect and M for the mesh. So this is also broadband technique, and it's quite similar to the TRL technique, where the impedance reference impedance is set by the trim resistor, but it can also be used with the fixed probes. So and it combines this is actually it combines both the advantage as well as the disadvantages of the SOLT and the TRL respectively. So here is the details on the SOLT calibration, where short and the load they have the inductance value, and often have the capacitance value, and this can be negative also. And this method is mathematically overdetermined method, and it's available in most of in every VNA. So in case of the SOLT calibration, all the standard must be perfectly known. And the TRL calibration is you can see the S parameter are they are referenced to the Z0 line. So here in this case, the reference plane at the center of the through. So reference plane is the this center of the through, and these S parameters are referenced to the characteristic impedance Z0 of the line. So Z0 is inherently complex at low frequency, and this method requires least information about standards in compared to the SOLT calibration, and this method is more accurate, however, and we can use this method if we do not have the calibration standard in same type of same connector type as our device under test. And this method is not much suitable for fixed probe spacing, such as in the probe cards. So the another method is the LRM or LRRM calibration method. This is similar like the TRL, and here only and the another term is the mesh, which acts as infinitely high loss line, and for this the through or delay for the through line or delay, the mesh resistance must be known, and in this case also the measurement reference to the laser trim resistor, and this is same as the same standard as SOLT only, so no need for the culprit. So once we understand the measurement setup, its devices, key components, and the calibration methods. We also need to verify the calibrated data or calibrated signal from the device under test for for the verification purpose. Especially some parameters are already set for different um, already set. So in case of the through, reflect, and the mesh, we need to reference the calibrated data with these some parameters for the calibration verification. So in case of the through or delay, through the unity gain, 1ps line, and a phase lag are the key parameters for verification. And in case of the reflect, the unity gain and a negative capacitance are the key parameters for the verification. And for the mesh, generally standard 50 ohm load is used on the probe, and the transmittance parameter S21 is measured. So this is the final comparison between the calibration methods, in the SOLT, TRL, and LRREM method. So in case of the SOLT and LRM, in both the cases the Z0 is referenced by the trim resistor, whereas in TRL this is Z0 reference to the transmission line. So the probe card support is not possible in case of the TRL, and in terms of the accuracy, the LRM, the TRL method is the best method. So the another important aspect of the power handling measurement, another aspect of the measurement system is the power handling measurement. Power handling measurement is the limit actually which determines the power handling capability of the IPD devices. So beyond this level, the device may get damaged. However, still there is some safety that the dynamic range of the power handling limit is far beyond the dynamic range of the system. So in order to minimize the losses due to the damages that may occur due to the power level, generally power dividers and low pass filters are used next to the power amplifier, so they can split the power or remove any harmonics. So it is important to know the power handling capability of the device, especially in case of the power divider and the low pass filter. So in this block diagram, this is the typical measurement system block diagram for the power handling evaluation of the power divider, which is fabricated on the silicon gallium arsenide substrate. In this case, so here is the device under test, and at the input of this device under test, minus 20 dB coupler is used, which measures the incident power from the amplifier, and at the output, minus 40 dB attenuator and a spectrum analyzer is used to measure the output power. So in this case, the initial test was carried out with 3.5 watt of continuous wave RF power, which is injected at the input, and then after 10 hours of continuous operation, the power was increased by 2 watt at 2 watt at each step. So these are the power handling data of the power divider. So after continuous operation, of the 60 hours, so due to the good thermal conductivity and of the power divider on gallium arsenide substrate, this power divider endured up to 12 watt of incident power during 60-hour step test. So we can see the 4, 8 and 12. So 12 watt of incident power, input power, is endured during the 60-hour of the step test. So these are the power handling measurement results. So the last and what the most important aspects of the IPD measurement technique is the process control monitoring, PCM. Process control monitoring is the process used to obtain the detailed information about the processes used while the measurement is carried out, where the PCM is associated with the design and fabrication of special structures needed for the monitoring test structures, and these structures are especially placed over across the wafer at a specific location along the chip produced, and thus we can have the closer look into the process variation. And PCM data is collected and statistically analyzed, and we can use those predetermined specification to compare these data, PCM data, to identify whether the wafers are good. And in the fabrication process, especially the semiconductor fabrication process, the PCM tests are used to ensure the process stability, where the process shifts are monitored. So in case if the fabrication process is out of control, PCM measurement will capture it. So in this case we can see the wafer fabricated at the RFIC lab, Kwangwoon University, which includes the 5 PCM over the single silicon wafer at different locations, and their structure, PCM structure. So in PCM, the number of die per wafer depends upon the wafer size and the location and the cost. Each PCM die it consists of multiple modules with different test structures to be measured. So the wafer quality and the long-term reliability of this device are determined through these measurements. So at the conclusion, we can say the IPD is an important RFIC fabrication technique in order to achieve the high circuit density, miniaturization in the size, and to minimize the cost of as well as for the high precision. And it's a bridge platform between the front and the back ends of the semiconductor industry. So for monitoring the overall performance, we need to have the good knowledge of the measurement techniques and the components used for the measurement, as well as the precise measurements are necessary for monitoring the overall performance. So in order to ensure the reduction in size and to reduction in the noise, on the on-wafer measurement, power handling measurement, and the process control monitoring are the key aspects to remember. So these are the references, and thank you for listening.